Okay, I'd like to introduce our next speaker, Matthew Bandelt. Dr. Bandelt joined the New Jersey Institute of Technology in July 2015 after completing his PhD at Stanford University. His background and experience are in the behavior and modeling of ductile cement-based materials, performance of recycled aggregate concrete, and durability of reinforced concrete structures. His research has been supported by the National Science Foundation, state and federal transportation agencies, and private companies. Matthew is the recipient of the NSF's Faculty Early Career Development Award and the NSF Graduate Research Fellowship. He is a licensed professional engineer in New Jersey and Pennsylvania and is heavily involved in the American Concrete Institute, holding voting positions in numerous committees.
Thank you. Hi, everyone. Nice to be with you. I was excited to be invited to speak here. I actually was thinking about the first presentation I ever gave at a conference, and it was actually, I traveled to Tokyo at Tokyo Institute of Technology back in like 2012 or 2013. And I went there and I gave my presentation and I plugged my computer in and my computer shut down. And so now I am here a decade or so later, and I'm excited to be here. So what I'm going to be talking about today is the use of highly ductile concrete materials and their applications to structural components and systems for seismic design. This will sort of walk you through some research over the last 5 or 6 years within my research group. And then I'll also begin to explain some research that we have going on right now and research that we have planned out over the next 4 to 5 years through a project sponsored by the National Science Foundation. So in terms of the highly ductile concrete materials that we're talking about, basically what we're referring to is fiber reinforced materials that may have a range of different mechanical properties. Generally speaking, my research group has been interested in materials that maybe have tensile strengths from 2 megapascals all the way up to 10 megapascals in terms of tensile behavior. The compressive strengths of systems that we've studied have ranged from, say, 40 megapascals all the way up to 120 megapascals, some of these ultra-high performing materials. But the general trend in all of these materials is that in comparison to concrete, they all exhibit either a sort of pseudoplastic type behavior in direct tension or a strain hardening type behavior. The research in this field has evolved significantly over the last decade or two. So here's a study from 2011 where they looked at the use of HPFRCC materials in coupling beams or link beams to reduce the amount of shear and longitudinal reinforcement that goes in those members. One of the things that they found from that study was the big improvements on constructability while also maintaining really excellent structural performance. In general, one of the things that we get when we use these types of materials and we subject them to lateral loads is really improved damage tolerance as well. So in traditional reinforced concrete elements, we can get to a large amount of spalling and other forms of damage when we get to high levels of lateral displacement. And the reinforced HPFRCCs, what you see is less of that, right? The material holds together very well in compression, in diagonal tension as well. And so we see less damage at large levels of deformation. One of the things I'd like to take you through is an example of how HPFRCCs have grown in one sector of the construction industry. So the Federal Highway Administration has put together on their website a nice sort of data set of the use of UHPC in transportation structures, specifically bridges. And so over the last few years, they've just documented every bridge or not every bridge, but a lot of bridges where UHPC has been used. And it's grown substantially in the bridge construction sector. So what you're looking at on this graph on the x-axis is just time from 2006 out to 2020. And on the y-axis is the cumulative number of bridges that have used these materials in the United States. And what you see is, a slow and steady rise up to about a decade ago, and then there's been this very dramatic increase in the use of these materials. But one of the things that, that I've been interested in is what are some of the obstacles that have prevented growth in the seismic design arena. On the building side, we don't have a repository like this that the Federal Highway Administration has on the bridge side, but I've just been interested in the seismic design aspects of why some of these materials have not been grown at the same rate. So these materials have been studied in a range of experimental seismic-related research. I'm showing them highlighted in particular regions. It doesn't mean that you would necessarily like precast with that, or they could be cast in place. But the point is like these are the particular regions where we think you could see some benefits. So one is in like plastic hinge regions of beams and columns where we would expect significant amount of damage. Anywhere where there's high combination of shear and bending, like at the base of shear walls. In coupling beams, there's the potential to reduce transverse reinforcement. There's also been research on using them as sort of structural fuses in different elements. And, you know, all of these basically are locations where we expect damage to occur under a seismic event. And provide benefits, whether it be through ductility or strength or damage tolerance, is sort of the avenue in which we are interested in exploring them. One of the things that I've focused on in my PhD, I mentioned earlier, I did my PhD at Stanford, so I was out here, lived in this region for a few years, and one of the things that we found during my work while I was a graduate student was that reinforced HPFRCCS, they fail in a very different manner in comparison to reinforced concrete. When you teach an undergraduate reinforced concrete class, you teach students that, you know, a member undergoes cracking first, then there's yielding of the rebar, and then eventually the concrete will crush in compression, right? That's the way we design for FLEXURE. In these reinforced HPFRCC systems, what you see is a different sort of failure mode. And so on the x-axis here, what you're seeing is different types of failure modes, so shear, crushing, buckling, and the last two are categorized as reinforcement fracture and fiber bridging failures. And on the y-axis, these are just different levels of deformation that caused failures. And they're from a range of large-scale monotonic and cyclic experiments. But the key here is that most of the loss of flexural capacity with these reinforced members doesn't occur due to crushing. Instead, it occurs due to something that happens on the tension side of the element. So, you know, it's sort of a rethinking of how we think of failure, right? So if failure is happening due to fracture of the bars, or the fibers pulling out at a cross-section resulting in loss in load carrying capacity, this necessitates a rethinking of how we predict strength, how we use modeling tools, all these sorts of things to account for a change in failure modes. In terms of the reason why these reinforced elements sort of fail on a tension side really has to do with how the fibers prevent splitting cracks from forming. And so this is from a while back looking at what are called tension stiffening experiments. So what we have here is just a prism of reinforced concrete element pulled in direct tension. So there's a single bar that's pulled in there. And basically what you see is like a long length over which the deformation spreads out. And then looking at a few different HPFRCC systems, the deformation concentrates significantly differently. So here what we see are like these long splitting cracks, whereas with the HPFRCC system, you don't see quite the same thing. And so the deformation sort of concentrates in a direct tension manner in a different way. And so as a result, in direct tension, these would potentially fracture at lower levels of deformation. Now, that doesn't necessarily correspond one-to-one when you go to a flexure state, but that's what happens. And then looking at another type of HPFRCC system, it happens in an even more concentrated manner. And so when you look at like load versus the strain of that specimen, what happens is if the red line is just a typical reinforcing bar, the black line is the tension stiffening that happens in a reinforced concrete member. These other two lines represent two different types of HPFRCCs, and basically you activate a lot more strength early on, but on the flip side, in direct tension, you shorten that displacement capacity. And so this just sort of necessitates like a rethinking of what happens So if you know what happens in direct tension, what does this mean in terms of flexure? And so these are from two sets of experiments. One's for a reinforced concrete element, and one's for a reinforced HPFRCC element. And what we're looking at is just applied load versus displacement. And so both of them generally go through a load level that induces cracking. Eventually, the steel will yield. And then the reinforced concrete, the member fails due to crushing, and what happens is we return to the steel cage. In the HPFRCC element, there's a loss of HPFRCC tensile strain capacity. Eventually, those fibers, they don't bridge a crack at some point. And there may be a little bit of drop in load, but that sort of continues on. The difference is with the reinforced concrete, basically you crush and you return to whatever the steel cage is, whereas with the HPFRCC, you can continue on until eventually the steel fractures. And that's partly that's because the concrete holds so well together in compression that you don't lose that strength due to compression. You continue on until eventually the steel bars fracture, you get another type of failure mechanism. So a colleague of mine, Yi Xiao, he looked at sort of what controls these failure mechanisms, and so he came up with a term that he called omega, and that was a ratio of the steel strain hardening capacity of the longitudinal bars related to how strong the tensile capacity is. And so basically what he found when he looked at a whole host of these experiments was that as this ratio increases, you move from a more localized failure to a more ductile failure that extends and sort of activates that rebar. And so he found this across a range of different experiments, and basically what happens is as that ratio increases above 1, you significantly increase the displacement capacity that you can get out of an element. What all of this leads to at like a component level in terms of changes in failure modes and displacement and these sorts of things, what I've been interested in is how does this then affect a seismic system level design, analysis, et cetera. So, we have structural models that we use. Generally, we might use lumped plasticity models in design or something with a little bit of distributed plasticity. So those might be like fixed length hinge models or spring hinge models. But a lot of these basically rely on, maybe moment rotation in the case of spring hinge models. And so if we switch from like reinforced concrete where things fail in flexure due to crushing to these new systems where they fail in a very different way, they have different strengths, et cetera, how do all the existing models that we have for reinforced concrete, how do they apply when we go like that next level up if we want to go and use these more in systems as opposed to just individual components? And so we looked at this, and we basically what we found was that the traditional approaches that we use for reinforced concrete don't work well for HPFRCCs, and I'll give you a couple examples. So on the x-axis here, what we're looking at is rotation capacity of different experiments in the literature. And on the y-axis are rotation calculations using things that have been developed for reinforced concrete. So this is from Pauly and Priestley, from Panagatos and Fardis. We have a paper from 2019, and we looked at a whole bunch of things that have basically been applied for reinforced concrete, and they just don't work that well for reinforced HPFRCCs. And this makes sense, right? They weren't designed for that, right? They were designed for failure mechanisms that were different. And so this got us thinking, like, we need to account for failure modes, ductility, distribution of damage when we are analyzing members that have this very different type of behavior. So can we follow the process for how we've built models for reinforced concrete? Well, what's the process? Basically, what we typically do is we execute a series of experiments. We repeat across a number of variables, change reinforcement ratios, change the type of element, shear span to depth ratio, what concrete we're using, et cetera, and then we fit a model to it. The challenge is when you use like UHPC or any of these fiber reinforced concretes is there's limited existing experiments. It takes a lot of time and money to create a large database when you're using new materials. And the material properties are rapidly changing. So There's lots of new materials that are coming out with different mechanical properties, different types of fibers, all these sorts of things. And so this creates some challenges. So what I did with some of my prior students was we took an alternative approach. And so rather than relying on physical experiments, we started by relying on numerical simulations. So we used some advanced finite element models that we had previously validated on experiments. And rather than, so that was like our starting point. And then we repeated across those same sorts of variables. And then what we did is we fit a model to it, okay? And so at this point, you'd say, okay, well, you fit a model to a computational tool. So like, does this work well? So then what we did is we validated against a separate set of physical experiments. And what we found is we can really predict well using, so computational tools are our starting point. We work through the process, and then we validate on physical experiments. These are all physical experiments, but on a smaller data set because we don't have the same data set that we would have for reinforced concrete. And here what we see, so rather, like in the last slide I showed you all the data points for reinforced concrete were like way up here. We're seeing like much better agreement between a prediction and, between the physical experiments and our predictions. So this shows us that when we use some high fidelity computational tools, finite element tools, we can use those as a great resource as opposed to starting with physical experiments. So we sort of flipped the order in which we do things. Then what we did is we used some of this knowledge for predicting rotation capacities and applied it more at these component level members. So in a component member, we try to lump the plasticity in a particular location. So in this case, we used nonlinear springs. It had a rotational model that had different levels of degradation based on the cyclic displacement history. We set some sort of sets of targets to match physical and physical experiments, and then we compared those to the experiments. And so we have a paper out on that where we built some of these tools and simulated a range of physical experiments. And we primarily focused, so I'll pause here and say this focus has been on members without axial load, and that's because there's even less data on members with axial load in some of these situations. So we started with members without axial load, and I have a current phase of research that's looking at members with axial load. So I forgot to mention that earlier, but that has primarily been our focus. And then what we did is a design illustration of a 4-story frame structure. This is from a work from Kurt Hazelton that he designed a code-conforming building back about 15 years ago, and it's been used on a range of experiments for benchmark studies. And we came up with 2 types of scenarios. So the first scenario was, what if we just went through and we replaced one for one in those beam elements these HPFRCC systems? So I didn't really think about what might happen exactly, but if I just went and I replaced the material in like a one-for-one member. And these could be precast or not. They could be cast in place, and the lines in between those orange regions could all be HPFRCCs. But the point is just, what would happen if we did this? And the second thing that we did was we replaced the HPFRCCs, or replaced the reinforced concrete with HPFRCCs, but now we started to account for changes in strength and ductility and these sorts of things. So, basically what you see is smaller section sizes as we go from case 1 to case 2. So our seismic system analysis, effectively what we did was we started with sort of this archetype model. We then subjected them to different earthquake records. So we did a incremental dynamic analysis. So we had a range of earthquakes across different intensities that we looked at. And then what we did is we looked at the observed response in terms of deformation on the x-axis and earthquake intensity on the y-axis. And here are some of the results that we see. So we're looking on the x-axis is just the story drift ratio. In this case, it's basically just how much has the system moved versus, in this case, it's the spectral acceleration divided by the spectral acceleration at the maximum considered event. And what you see here, the red line represents the median response, but each one of these lines is a single earthquake record that's increasingly scaled. So basically, once you get to a certain scaling point or a certain spectral acceleration, the displacement just sort of goes out to infinity, and that's basically the structure collapsing. But in that, when you compare the reinforced concrete to just that first case, you see this line sort of goes down, right? So if I drew a horizontal line, that line goes down. And that's mostly because I hadn't considered the effects of how the strength would influence the strong column, weak beam ratios. And then when I look at where this flatlines versus where this one flatlines, this one goes up. And I'll characterize this with some numerical statistics in a second. But the point is basically the capacity of the structure, or the collapse capacity of the structure, moves up when I use these materials. So here are representations of under a particular ground motion, the amount of damage that occurred. But when we looked at a range of scenarios, basically what we found was when I didn't consider the effects that the materials have on strength, the structure was more likely to collapse, so that case 1 HPFRCC frame. But then when I sort of went through a thoughtful engineering design process, it was about 40% less likely to collapse under the maximum considered event. So significant improvements in terms of life safety, and we know there's other benefits as well in terms of damage tolerance and these sorts of things. We repeated this in a recent study looking at different types of frames, so space frame buildings and perimeter frame buildings. We looked at it across 4, 8, and 12-story frame structures. And basically, on average, what we found, and it varied from space frame to perimeter frame buildings, was that we would see roughly a 20% on average improvement in terms of probability of collapse under the maximum considered event, and significantly lower mean annual frequency of collapse as well. So there's potentially a lot of really great improvements that we can have when we use these materials in terms of safety. We also looked at how does the use of these materials influence the overall concrete that we use, the volume of concrete, and the rebar tonnage. And so this is, on the y-axis, is the reduction in concrete volume that we had in these systems versus the number of stories. And P represents perimeter frame, and S represents space frames. But we saw anywhere from, on the high end, about a 14% reduction in the overall concrete volume. And so far, we've only looked at the beam elements. We're now working on column elements as well. To the low end, a 5-10% range. We also can significantly reduce the overall rebar tonnage in a structure. So now there's flip side effects because you're going to use fibers, but the rebar could go down from down 5% all the way up to 25% reduction in longitudinal reinforcement, not even considering the benefits you can get from shear. But all of that was premised on the fact that there's limited experimental data on members with axial load. The system level analysis of structures with materials and components beyond beams is something that we've been interested in. And there's other variables that we sort of are interested in considering. So how does one of these fiber reinforced systems compare to another? What are the implications in terms of cost or environmental impacts? So we have an ongoing study that's supported by the National Science Foundation. And one of the first things that we're trying to do is just investigate elements under the combined loads of axial load and lateral loads. And that's really not to, there's been some work in this area, but we're trying to fill in some gaps that are in the literature. We'll then be taking that and basically repeating the process that I went through for beams. So we'll develop some plastic hinge models for that, then assess the system level performance, and then we'll use that to quantify things like system level losses, life cycle costs, all these sorts of things. And so we are here in terms of this project. It started in August or September of this year. So we're starting some experimental work now. Before we started the experimental work, we used some computational tools to help us just guide our experimental program. And so we looked at the effects of different axial load ratios on columns. So ranging from 0% axial load, which is basically just a beam, all the way up to 25% axial load, at least just in the simulations that I'm showing here. And what we see is as I increase the amount of axial load, I get increased strength. That's pretty typical with like a PM interaction diagram. But I also get increased displacement capacity, and that's because basically as I apply that axial load, I'm relieving some of the tensile strains that would be in the rebar, and so that lets me displace the member more. And so that's the effect that you see as I go from the purple line out to the green line. And then eventually I get to a certain axial load ratio, and I begin to transition back. So I begin to lose displacement capacity. And that's because basically the axial load can increase deformation capacity up to a point, but then I transition from this tensile fracture phenomenon and back into what would be a little bit more traditional for reinforced concrete. So in ASCE 41, they have predictions in terms of plastic rotation versus axial load ratio. And basically what happens is as I increase the axial load ratio, I reduce the amount of plastic rotation I assume I'm going to be able to handle, right? So more axial load, less assumed rotation capacity. Our numerical, I just said that. Our numerical study, basically what we did a relatively similar thing, but if I look at a particular reinforcement ratio, so say 1.25%, as I increase the amount of axial load, I move from like this green, which is say 12% plastic rotation, to a yellow, which is a little bit higher, et cetera. So basically what's happening is I'm getting more displacement capacity as I increase axial load, and then see right here around 15%, it begins to go back. So it's this is preliminary from some of the numerical studies that we have, and we're starting experimental work on this to validate whether or not this is just a numerical thing or whether we see it experimentally as well. So those are some of the gaps we're trying to fill in the literature. And so in summary, if you had a few takeaways, the first would just be when you use these fiber reinforced systems, it changes the failure modes of individual components, and that maybe will play into seismic analysis and design of structural systems. There's significant potential to improve life safety and damage of individual elements when you properly engineer these systems. And then there's some new ongoing work related to sort of expanding beyond flexural elements into members that are more beam columns where you have axial load, and so that work is just beginning. So with that, I thank you and thank the sponsor, and if there's any questions, I'd be happy to answer them.
Thank you very much. I have two, I think, simple questions. The first one is in your seismic analysis, do you have some conventional reinforcement in your ultra?
Yeah. So they'd all be reinforced with longitudinal steel at relatively similar reinforcement ratios. You can reduce the section size, width, and get some benefits from that. But yeah, we didn't change that portion of it. Yeah.
And the other question, these were numerical studies, not on a real shaking table.
Correct. Yeah, we have some physical experiments that are upcoming, not on a shake table, but they're more at the component level. And then for the the frame systems, we're using lump plasticity models, so they're numerical. Yep.
Thank you very much.
Yeah. Hello.
Hey, I was kind of shocked to see the result for the rotational capacity using the existing model.
Yeah.
That prediction was so bad. It seems to me like your prediction is overshooting.
Yeah.
As an experiment. Why does that happen?
Sure. So basically, it's one of two things. So the first is if you account for the fact that the member is going to fail due to on the tension side of the element. It's a very different phenomenon than failure due to crushing of the material, right? So you get just a much different amount of rotation that you can have because the concrete can go so much further because it won't crush. The second thing is that the actual plastic hinge length is very different. So like if I go back to maybe slide 2, the damage occurs at a very small region here. So that once you localize a crack, basically, all that deformation goes into a really small crack. Whereas the damage is, it's roughly equal to the depth here, right? I can see the damage is spread out quite a bit here. So you get better sort of crack control under service states, but once you localize that crack, it changes things. And so the combination of those two things just drastically makes it so that the existing reinforced concrete expressions don't really work.
Seems to me like those existing model is predicting the left-hand side behavior.
Correct.
And then your experimental result is kind of showing your new material is much smaller, like a rotation capacity.
So it's higher rotational capacity is what we get. So the experimental results are a lot higher. Now one of the plots that I showed was based on the fact that if you were to use one of those models, you'd have to assume that the bars fracture as opposed to the concrete crushes. And so it effectively just doesn't sort of logically kind of keep going down in that manner.
Thank you.
Yeah. Yeah.
So in the concentrated plasticity model that wouldn't be a typical frame model that would be used, right? Frame model that would be used. Would have to, what parameters were changed from the first frame?
Sure. So you're taking you're concentrating all the plastic hinge or all the deformation into a spring hinge, and that spring hinge is defined by a moment rotation response. So that moment rotation response is, basically just a series of, say, 4 moment points and 4 or so rotation points. So you could use like one of the CSI products. In this case, we used OpenSeas because it's a little bit more robust for research purposes. There's some additional work because we included like a degradation parameter and these sorts of things to account for some of that. But it's the type of thing that could be implemented in a commercial structural analysis program. Yeah.
But in a commercial software, I know you would love to see this being implemented in more places, right? So in a commercial software,
Yeah.
do you think that would be a different parameter that we input, and would that parameter change with different cases, with actual standards, and obviously with actual tools?
Yeah, so there's no, because like a moment rotation hinge is available in a lot of commercial software packages. There's no reason that you couldn't, take the general rules that we applied in the OpenSeas research setting and move it into a commercial platform, yeah.